Good afternoon, everybody. I welcome you all to this series of lectures on microprocessors and microcontrollers. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today, I am going to discuss about the DMA controller 8257. So, what is DMA controller? DMA controller means direct memory access controller. So, when we have to transfer the data between the memory and I/O device, for small volumes of data, the data is given to the microprocessor. Then from microprocessor, the data is routed to the memory. Okay, and we do a simple program. This can be illustrated by a simple program like this: move AX 200H. So that means AX register is initialized with the immediate data 200H. Then move DS AX. So the base address is stored into the data segment, or the data segment is initialized with the base address. Then move SI 500H. So SI register points to the location 500. Then move DX 600H. So DX register is used to point to the I/O device. For I/O device address, the DX register is used and in indirect mode of addressing. Then move CX 64H. Let us say I want to transfer 64H amount of data. 64H means 100 quantity of data. Then in ALDX, so that means I am getting the data from the memory location. I am getting the data from the I/O device whose address is 600H into the AL register. Then move SI AL. So the data which is obtained from the I/O device, first it is moved into the AL register. Then from AL register it is moved into the memory location. And like that, I have to transfer 100 bytes of data. So decrement CX, then increment DX, jump no 0 up. Jump no 0 up. So this is up. And this is the end of the program. So here the data is transferred from the I/O device to the memory. For small volumes of data, you can transfer from the I/O device to the memory involving the CPU. But in case you have to transfer a large bulk data, then it is unnecessary that the data is being brought to inside the microprocessor. So the data can directly be transferred from the I/O device to the memory using DMA. So that is why it is called direct memory access. So if this is the memory and if this is the I/O device and if this is the CPU, so in this program what we have done, we are taking the data inside the CPU. From CPU we are moving the data to the memory. So if large volume of data is involved, it takes a lot of time and delay by involving the CPU because the path involved is more. So in that case, DMA is used wherein the I/O device is in direct contact with memory and the memory and I/O device can communicate each other for the transfer of large volumes of data. That is called direct memory access. Okay. Now I'll give you a more detailed block diagram for the DMA. So this is the microprocessor 8086. Okay. And for I/O device transactions, we use only the 16 address lines. You know that 8086 has 20 address lines, but for I/O device purposes, only 16 address lines are used. So that means we are going to use only AD02, AD15. And this address latch. And these are the AD02, AD15 address lines. And this is a ALE signal. You know that AD02, AD15 address lines are time multiplexer lines, and during T1 address is available on these lines, and during T2, T3, T4 data is available on these lines. So during T2, T3, T4 the same lines are used for the transfer of data. So when address is available on these AD0 to AD15 lines, ALE signal goes high, and this is used to latch the address on the address buffer registers. So this is AB address bus, and let's say this is the memory. And this is the I/O device. You can also call it as the peripheral device. Peripheral device. So this address, this is address bus A, and we have the DMA controller, which is nothing but 8257. I'll explain the sequence of operations after completion of the block diagram. This is A dot B means address bus. And during T2, T3, T4, I mentioned that data is available on these lines. So here, data is available on these lines. And this is we have three buses in any microcomputer system. What are the three buses? Address bus, data bus, and the control bus. And the control bus CB. And this control bus basically contains I/O read, I/O write, memory read, and memory write signals. So I/O read and I/O write and memory read and memory write. These are the control signals. So the peripheral device, whenever it requires the system bus for the DMA transfer, it sends DMA request to the DMA controller. It sends DREQ signal to the DMA controller. So this is an active low signal DREQ, which is sent by the peripheral device whenever it wants to do the DMA operation. And when DRQ signal is given to the DMA controller, it sends hold request to the microprocessor. So this is a hold signal which is given by the DMA controller. And here it is hold and here it is HREQ. So the DMA controller sends hold request signal to the microprocessor. And when the microprocessor acknowledges the DMA request, it sends hold acknowledge signal to the DMA controller. So this is called HLDA, hold acknowledge signal. And the DMA controller, when it receives hold acknowledge signal from the microprocessor, it sends DACK0, DMA acknowledgement signal, back to the peripheral device. So this is called DACK0. So this is called DMA acknowledgement signal. So you see here, initially the switches are in the positions, up positions. So this is A positions, A. And the microprocessor or the microcontroller is in total control of the system bus. And when the peripheral device sends the DMA request by activating DREQ signal, then the DMA controller sends HREQ signal, and the microprocessor responds by activating HLDA signal, and the DMA controller activates DACK0 signal. So when DACK0 signal is activated, then the peripheral device and the memory modules, they come in direct contact, and microprocessor is disconnected from the system bus. And all these switches, they fall down to B position. So all the switches, they fall into the B position, and the microprocessor and the memory and the peripheral device, they come in direct contact, and the transfer of data takes place. So when the DMA is completed, then the peripheral device deactivates DREQ signal, then the DMA controller passes the signal to the microprocessor, and microprocessor deactivates the hold request, and the microprocessor again gains control over the system bus after the completion of the DMA operations. So here the advantage of DMA is it facilitates fast transfer of data between the peripheral device and the IO peripheral. So it facilitates fast transfer of data between the memory and the peripheral device. So when the DMA is not performed, the switches are connected in such a way that the microprocessor is connected to the address bus, data bus, and the control bus. When DMA is performed, the switches, they change position, and the address bus, control bus are connected to the DMA controller, and data bus gets isolated by the CPU, and it is connected directly between the IO and the memory. So this process is called as direct memory access. And for DMA, we use a special purpose IC that is called 8257 DMA controller. And the prominent features of 8257 are, this has 4 channels, and which can be used for 4 IO devices. So each channel, it has a 16-bit address and 14-bit counter. And the channel can transfer 64 kilobytes of data. And each channel can be programmed independently. And the channel can perform read transfer, write transfer, and verify transfer operations. So for that, we use mode register and status register. The formats are shown in the next slides. And this DMA controller, it generates the mark signal to the peripheral device after 128 bytes are transferred. So in total, we can transfer 64 kilobytes After transfer of every 128 bytes of data, it generates the mark signal. And the frequency range of 8257 is 250 Hz to 3 MHz. And it operates in two modes, master mode and slave mode. So what is slave mode? Slave mode is used where the DMA controller is a slave and CPU 8086 is the master, and this is used to program the DMA controller. And in master mode, the DMA controller is in control of the system bus and the peripheral device and the memory. They come in direct contact for the transfer of data. So this is the 40-pin IC. 8257 is a 40-pin IC and it is available in DAP, dual line package. We'll go to the block diagram of 8257. So this is the data bus buffer D0 to D7 and 8 pins are dedicated for this. And read-write control logic, it has IO read, IO write, clock, reset, and A0 and A3 signals. And these A0 and A3 signals, they are used to address the 4 available channels. And also we have the ready signal, HRQ, HLDA, memory read, memory write, AEN, and address strobe, TC, and mark signals. And there are 4 channels. So these are the 4 channels, channel 0 and channel 1 and channel 2 and channel 3. So this is the priority resolver. See, if DMA controller can receive the DMA request on these 4 channels, and when channel 0 has highest priority. When DMA request is received concurrently on all these 4 channels, then channel 0 is given high priority. And after that, after channel 0 is provided service, then channel 1 is given control over the system bus. And each channel, it has 2 registers, address register and the counter. The formats I am going to discuss in the next slides. And we have already discussed about the HRQ signal and HLDA signal and DRQ signal. So DRQ signal is received by the IO device. When the IO device gives the DMA request, then the DMA controller sends HRQ signal, hold request signal, to the microprocessor, and microprocessor acknowledges the DMA request by giving back the HLDA signal. Then the DMA controller gives DMA acknowledgement signal to the IO device. And clock signal is normally connected to the system clock. And mark signal, we have already discussed. After transfer of every 128 bytes of data, this mark signal is activated. So each channel, it has 2 registers. First is the terminal count register. The format of terminal count register is like this. It is a 16-bit register. It is a 16-bit register, and this is B0, and this is B13, and this is B14, and this is B15. So this B0 to B13, they are used for to count how many bytes have been transferred. So they provide the terminal count. So B0 to B13, there are 14 bits. So 14 bits means how many bytes? 2 to the power 14 bytes. So that is equal to 2 power 4 into 2 power 10 bytes. So that is equal to 16 kilobytes. So they provide count for 16 kilobytes. And the uppermost 2 bytes, they are used for to verify the status. So if it is 00, B15 and B14, If it is 00, it means that you are verifying the transfer. Verifying the transfer. If it is 01, then it means that it is performing the write operation. And if it is 10, it is performing the read operation. So they indicate the transfer of data over the system bus, whether the data is flowing from the IO device to memory or from memory to the IO device. And 11 is invalid. So these are terminal count register B0, this is B1, B2, and so on to B13. This is a format of terminal count register B0. And the mode set register format is like this. It is a 8-bit register. AL. First one is AL. So AL means if it is 1, it enables auto reload. That is the purpose of AL. Then TCS. TCS is stop DMA on the terminal count. So terminal count stop. And EW is extended write. See, for performing the operations on slow devices, the extended write. So one cycle extra is, one clock pulse extra is added so that slow devices are accommodated. And RP. RP is the rotating priority. So the default priority is channel 0 has highest priority and channel 3 has the lowest priority. And after channel 0 is given provided service, then automatically channel 2 is given, channel 1 is given the priority, and this priority can be changed by programming the rotating priority. If it is 1, it is a rotating priority. If it is 1, it is a fixed priority. Then enable 3, and this is enable 0. So enable 0 means it enables the channel 0. If enable 1 means it enables channel 1. Enable 2 means it enables channel 2. Enable 3 means you can enable the DMA channel 3. So AL means it is, if it is 1, it enables auto reload. If it is 0, it disables auto reload. And TCS, if it is 1, it is stopping on the reach of the terminal count. So stop on terminal count. And RP is the rotating priority, which I have explained you. If RP is equal to 1, then it is rotating priority. If it is equal to 0, then it is fixed priority. Now let us go to the format of the status register. So using the status register, you can find out whether the individual channels have reached the upper limit of the terminal count. So the format of status register is like this. It is also an 8-bit register. is up. If it is equal to 1, it means that channel 2 is reloaded from channel 3. So if you put this as 1, so that means that channel 2 is reloaded from channel 3. It is 1. And if TC, this is the symbol for bit for TC0, this is for TC1, channel 1, and this is for channel 2, and this is for channel 3. So as there are 4 channels, so you have the 4 bits. So if it is, this indicates whether if it is 1, it indicates that channel 0 has reached upper limit. Has reached upper limit. If TC1 is 1, it means that channel 1 has reached upper limit. Similarly, if TC2 is 1, it means that channel 2 has reached the upper limit, and similarly for channel 3. And the address configuration is like this. I told you that in the functional diagram we have 4 signals: A0, A1, A2, and A3. And if all these bits are 0, 0, then we are going to address the channel 0. And for count register, the address is 0001 for the channel 0. Similarly, for channel 1, the bits are 0010, and for channel 1 count register, the bits are 0011. And for channel 2, 0100, and for channel 2, 0101, and channel 3, 0110, and for channel 3 count register, it is 0111. And mode set register, which is a write-only register, the address is 1 followed by all zeros. And status register, which is a read-only register, the same address, 1 followed by all 3 zeros. So this is in brief about the DMA controller. So the DMA controller is used to save time instead of involving the CPU unnecessarily for the transfer of large volume of data. So as you said, initially the switches are in upward position A, and the microprocessor is in control of the system bus, and any transfer of data is required between the IO device and memory. The device has to send the data to the CPU, and from CPU only it goes to the destination. And as I have explained you, whenever DMA is needed, then the peripheral device sends DMA request to the DMA controller, and DMA controller in turn sends hold signal to the 8086 processor, and 8086 processor sends back the hold acknowledgement signal, and subsequently the DMA controller gives DACK0 signal to the peripheral device, and all these switches they fall back to the B position, and the peripheral device and memory they come in direct contact and for DMA process. And the DMA controller 8257, it is a 40-pin IC, and it has 4 channels, and each channel has 2 registers: address register and the count register. And we have a data bus buffer, and also we have the read-write logic, and we have the pins A0 to A3, and also we have the pins A4, A5, A6, and A7, and the ready signal. And the ready signal is used to accommodate the slow devices. So when the devices are slow, extended write signal is used for the DMA operations. And other control signals are memory read, memory write, and IO read and IO write. So this is IO read and IO write, and memory read and memory write. And we have discussed about the terminal count register, which is used to verify the type of activity, whether it is verifying the transfer or write operation or read operation, and you can involve 16 kilobytes of data, and this is the format for the mode set register. You can decide which channel you are using for the DMA. If channel 0 is used, then you have to keep this bit as 1, and AL is for auto reload, TCS is for stopping on the reach of the terminal count, EW is for extend write, and RP is for the rotating priority, and the remaining signals they enable or disable the respective 4 DMA channels. And this is for status register, which indicate whether any channel has reached the upper limits after the transfer of data, and this is the format for address for all the DMA channels accordingly. So with this, I conclude the today's session on the DMA controller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.